So I ask you guys a sincere, non-rhetorical, meaning I want an answer, question, which is, do you think that the temperature has any effect on the rate or speed of a chemical reaction? So I'll repeat the question. Do you think that temperature has any effect on the rate of a chemical reaction? So I'll give you guys just a few moments to think about this question and answer it. Okay, so we got a couple of answers now that the small talk is over. Kai says yes, and Kenan Crystal Wing says, yep, I think so. Well, congratulations to you because both of you are correct. The answer is yes. The rate of a chemical reaction is highly dependent on temperature. And this makes sense intuitively, right? Because what is temperature? Well, temperature is just average kinetic energy, right? And if the temperature of a system increases, well, the average kinetic energy increases. Kinetic energy, of course, is the energy due to motion. And if things are moving faster on average, it would seem to be more likely that they would react more quickly. So intuitively, it sort of makes sense, but how can we quantify the relationship between the temperature and the rate of a reaction? Well, it must be contained somewhere in the rate law equation. So recall that the rate law equation is that the rate of a reaction is equal to the rate constant K times the concentration of the reactant to the power n, where n is the order, 0, first, second, and so on. And so one of these two terms, either the rate constant or the reactant concentration, must contain something in it in which the rate is dependent on temperature. Now, the concentration doesn't seem like a likely candidate to include the temperature dependence because concentration generally doesn't depend on temperature, right? If you have like a 12 molar solution of some chemical, right? A 12 molar solution, and you heat it up, it's still 12 molar. There's nothing about that concentration necessarily that depends on temperature. And so therefore, it must be the rate constant. The rate constant is the factor in this rate law equation that includes the temperature dependence. The temperature dependence is contained in the rate constant. So another message in the chat from Kai says, I think an increase in temperature increases the rate of the reaction. And you would be correct, but then the question then becomes how, and how do we quantify that, right? And the answer is this equation right here. This is called the Arrhenius Equation. So I think Arrhenius was a Swiss gentleman. I want to say he was from Switzerland, and he developed this equation in a paper in the late 19th century. Kind of interesting to think about it. It was the 1800s, and this stuff was already figured out, even with their, I guess, compared to today's technology, primitive instrumentation, primitive communication. They still are able to figure this out. I just think it's cool how much they were able to figure out so early on in history. Anyway, so let's unpack this equation. This equation reads K, the rate constant, is equal to A times E to the minus E sub A over RT. So we're going to unpack each of these individual terms in this equation so that we understand it, because it's always important to understand things, at least in my opinion. As a student, I never wanted to just memorize a formula and just plug numbers in to get the right answer. I want to understand what exactly is going on here. And so I hope you feel the same way. So this term A here, that's called the frequency factor. We're going to go over that in more detail a little bit later. And then this whole term here, this e to the minus EA over RT, that's called the exponential factor. And we will discuss that in more detail shortly also. Now this e here, this lowercase e, that's called Euler's number. It's a mathematical constant. It's kind of like pi, it's one of those like non-terminating decimals that just keeps going on and on and on and on. And in your scientific calculator, you'll find a button on there that says e to the x. And so if you hit that button, it'll raise e to the power of whatever number you input into your calculator. So that's what this lowercase e is. And then over here we have this E sub A term. That's called the activation energy. It's also called the activation barrier, which is something that's really, really important, not only in kinetics, but also in thermodynamics. So it's very important that we have a solid understanding of that going forward. Got another message from JA. It says, hi, everyone. Hello, JA, and welcome. Good to have you here. By the way, if you guys find this valuable, I would highly appreciate you smashing that like button. So K equals A times e to the minus EA over RT, frequency factor, exponential factor, activation energy. There's a lot to unpack. And then in addition to those terms, we have R and T. R is the gas constant, and it's important to remember that R can actually have different values depending on what units it's in, right? So you might be familiar with R in the PV equals nRT ideal gas law equation, where R is equal to 0.08206 liters times atmospheres over moles times kelvins. However, the R that we're using, it's the same R, it's just different. It's reported in different units, so it's going to have a different number. The R that we're using that's applicable to the Arrhenius equation is this R, which is 8.314 joules over moles times kelvins. This is a constant. This will pop up over and over again, so it's a good idea, in my opinion, to commit this one to memory. And then T, of course, is simply the temperature. So this whole discussion has been on how does the reaction rate depend on temperature. Well, there it is, temperature, but it's got to be in kelvins. So if you're given a Celsius temperature on a problem or something, you must convert it to kelvins. Otherwise, you'll get the answer wrong. And I don't want that to happen. I love you guys too much for that to happen to you. I really don't want that to happen. So always make sure your units are taken care of. So let's talk about activation energy for a moment. So activation energy, remember that's the E sub A term in this equation. So activation energy, it's also called the activation barrier. It's basically like the maximum energy state of the particles that compose a system over the course of a chemical reaction. So for instance, let's say you have this reaction right here where you have two hydrogen molecules reacting with one oxygen molecule to produce water, right? Now, overall, this reaction is exothermic, right? The energy of the two water molecules down here is less than the energy of the reactants, the individual hydrogen and oxygen molecules. By the way, I kind of jumped ahead there. We have energy on the y-axis here, and then on the x-axis we have the progress of the reaction. So this is the energy of the system as the reaction moves forward, right? So notice that even though this reaction is exothermic, it's energetically downhill, so to speak, there's still an input of energy that must be made in order to get this reaction to go. And that represents the activation energy, this maximum right here. And this would represent what we call a transition state or an activated complex. So those two terms apply to the state of the reactants as they're sort of becoming products. So this would represent a state in which the bonds in the reactants have sort of broken apart and the bonds in the products have sort of formed. It's like a transition, like an in-between, right? In-between state, transition state, activated complex. Okay, so that's the activation energy. The energy that must be supplied in order to overcome the hump to get the reaction to go, even though this particular one is exothermic. Okay, so now we're going to talk about the frequency factor. So remember the frequency factor, that's the capital A in this equation. And the frequency factor represents the number of approaches to the activation barrier per unit time. And each reaction has its own unique frequency factor, just depending upon a variety of factors like the nature of the reaction, the shapes of the molecules, and whether the particular sites that are undergoing the reaction are hindered or inhibited by the rest of the molecule and things like that. So it's the number of approaches to the activation barrier in a given amount of time. But it's important to understand that not all approaches to the activation barrier are successful. Not all approaches to the activation energy result in a successful surmounting of the activation barrier and consequently result in the formation of products. In fact, most approaches, as this bullet point here shows, do not surmount the activation barrier. So that's the frequency factor. And then here we have the exponential factor. Now the exponential factor is this whole thing in red right here, e to the minus e sub a over RT. Now this number is between 0 and 1, and what it represents is the proportion or the fraction of the approaches that successfully surmount the activation barrier to form products. And if you play around with these numbers a little bit, you'll understand that when the activation energy is low and the temperature is high, then the exponential factor is higher. In other words, it's closer to 1 and further away from 0. So like I said before, it may be difficult to understand how this number works because it's a negative exponent, right? So if you think about this term right here, this minus EA over RT, that term will become less negative or more positive when the E sub A term decreases. So when this thing is low, this overall term becomes less negative or more positive. And also, if this number, this T, R, we don't really have to worry about it because it's a constant. It's the same regardless, right? It's the same no matter what. When the temperature is high, well, this term magnitude-wise gets smaller, but because it's negative, it becomes less negative. It becomes more positive, and so e to the whole thing, right, it's a negative exponent, gets closer to 1 when the magnitude of this term gets smaller. So I really hope that wasn't so confusing. I know it could be confusing. It kind of confused me. I had to read it a couple of times back in the day before I understood what was going on. But the main ideas here are that the exponential factor is between 0 and 1. It represents the fraction of the approaches to the activation barrier that successfully surmount the activation barrier, resulting in the formation of products. And the exponential factor is higher when the activation energy is low and when the temperature is high. So got another message in the chat from Kai. It says, I remember a little bit about activation energy. I don't know if I'm correct, but does it mean that with a low activation energy, chemical reactions progress faster? Yes, that's exactly what it means. That's exactly what it means. Low energies and low activation energy and high temperature means a faster chemical reaction. So if we look at this sort of graphically here, this represents what we call thermal energy distribution. And so this would represent a collection of molecules at two different temperatures, which we'll call T1 and T2, where T2 is higher than T1, or T2 is hotter, higher temperature than T1. On the y-axis, we have the fraction of molecules, and on the x-axis, we have the energy, right? So at any given temperature, right, a collection of molecules is going to have a distribution, almost like a normal distribution of energies. And notice what happens to the shape of the curve as the temperature gets hotter from T1 to T2. It kind of flattens a little bit, right? That's just the nature of temperature distributions. As temperature gets higher, the curve sort of flattens a little bit, right? And so over here, this dotted line here represents the activation energy. And so as we were talking about earlier, right, a higher temperature results in a larger fraction of molecules that can successfully overcome the activation barrier. So if I look at T1, let's say, right, that's the blue curve, right, and I look at the area under the curve to the right of the activation barrier, well, that's a pretty small fraction, right? That's a pretty small amount of those molecules that have enough energy to overcome the activation barrier, right? But if I look at the other one, right, if I look at T2, the temperature that's hotter, well, now all of a sudden I'm considering this entire thing here, right? And now it's still a very small proportion of the molecules relative to all of them that can overcome the activation barrier, but it's much higher than T1. And so we can see using this graphic representation that even we can see that even a small temperature, or a small change in temperature rather, results in a pretty profound difference in the reaction rate, because it results in a profound difference in the fraction of molecules that have enough energy to overcome the activation barrier. All right, so this is our last slide. It's just a problem that we're going to work out. And it says the activation energy of a reaction is 64.2 kilojoules per mole, and the frequency factor is 1.2 times 10 to the 11 inverse seconds. And it says to calculate the rate constant of the reaction at 25 degrees Celsius. So I like to start pretty much any chemistry problem by identifying the important relevant information. So activation energy, that's going to be important, right? That's the 64.2 kilojoules per mole. Frequency factor, 1.2 times 10 to the 11 inverse seconds, also very important. And then we need the rate constant, and the temperature is 25 degrees Celsius. So as you probably have already figured out by now, the equation that we're going to be using is the Arrhenius equation, which is K is equal to A, the frequency factor, times E, Euler's number, raised to the power of minus E sub A over RT, right? So let's identify what all of these terms are, right? So it says the activation energy, that's E sub A, that's our 64.2 kilojoules per mole. And it says that our frequency factor, that would be our capital A, right? That is 1.2 times 10 to the 11th inverse seconds. And then the temperature, that's T, is equal to 25 degrees Celsius. Now, if you were paying attention earlier, you would have picked up on the fact that the T in this equation here, the temperature needs to be reported in kelvins, right? So I'm given a degree Celsius temperature, I need to convert that to kelvins. And the conversion, it's actually pretty simple. If you have a degree Celsius temperature and you want to convert it to kelvins, all you have to do is to add 273. So 273 plus 25, that's 298 kelvins. That's our T. Now R, that's a constant. So remember R, right? That's 8.314, and that's joules over moles times kelvins. Got another message in the chat from Kai. It says, I don't know if you switched up your teaching style, but I am totally loving it. Oh, thank you so much, man. I really appreciate that, Kai. Right on. Thanks, man. It's nice to get some affirmation once in a while. All right. So we have activation energy, we have frequency factor, we have the temperature reported in kelvins, we have R, 8.314 joules over moles times kelvins. But notice something else. Notice that our activation energy is in kilojoules per mole, right? But R is given in joules over moles times kelvins. So that's going to be a problem if we don't do something about it. If we don't do something about it, right? So we can do one of two things. We can either convert R from joules over moles times kelvins to kilojoules over moles times kelvins, or we can convert our activation energy from kilojoules per mole to joules per mole. Now, personally, I don't know why. I couldn't tell you why, but I prefer to calculate the activation energy to joules per mole. So I'm going to go ahead and do that. So I'll do the conversion sort of in my head. Normally I would write these things out like as conversion factors and cancel my units and this and that, but I'm pretty sure you guys are advanced at this point, so I can just kind of skip ahead. So 64.2 kilojoules per mole is going to be 64200 joules per mole, right? 64,200 joules per mole is the same as 64.2 kilojoules per mole. So now we have all the information that we need, and we have units that are compatible with the equation, and we have units that are compatible with one another. And so at this point, the hard part is essentially done. At this point, all we have to do is to plug in the values into this equation up here, and hopefully I can do it without running off of the page. So I'll try to write small, although it's kind of hard to do on this little tablet here. Anyway, so we have the K is equal to A, that's the frequency factor, that's 1.2 times 10 to the 11 inverse seconds, times E raised to a big term, right? It's going to be negative 64,200 joules per mole. And that's going to be over the product of R and T. R, that's our gas constant, 8.314 joules over moles times kelvins. And then our temperature, that's 298 kelvins. So this whole thing is what we plugged our numbers into. So the next step is to make sure that our units cancel out here, and it looks like I'm a little bit off the page here, so I'm going to move this over here. Okay, apologize for that, guys. So we're going to make sure that our units cancel out, right? We have joules canceling with joules, we have moles canceling with moles, and we have kelvins canceling with kelvins. And so at this point, all that we have to do is to plug this expression into our calculator. Now, there's another thing I wanted to sort of suggest when it comes to problems like these. So this problem requires using scientific notation, and it also requires using the exponential e to the whatever, right? If you're ever going to be tested on a problem like this, make sure that test day is not the first time that you're going to be using your scientific calculator. Scientific calculators are kind of all over the place in terms of how they work, and what buttons you're supposed to press before other buttons and things like that. So make sure you understand the functionality of your scientific calculator before and you're comfortable with it before you're using it to bang out these calculations in the event of an exam. Because even if you know all of the theory, and if you know the formula, and if you know the units and all that stuff, if you don't know how to put it into your calculator, then it's not going to amount to very much. And that would be a really, really sad state of affairs. Okay, so at this point, plug those numbers in. Hopefully somebody watching this has already done it. That would be nice. And I would love to compare my result to whatever you got, but the result that I got is 0.67, and that is inverse seconds. It's inverse seconds because the unit of our frequency factor is inverse seconds, and the rest of the units canceled out. So, hey, hope you enjoyed the video. If you'd like to watch the full video from which this clip was taken, click the box over there on the left. And if you'd like to watch my entire chemical kinetics playlist, click the box on the right. Thank you very much for watching, and take care.